Welcome to the deep dive. Today, we're journeying out into the cosmos. We're going to explore some stars that are, well, a lot more dynamic and maybe mysterious than our own sun.
Right.
Imagine trying to figure out what's inside a really complex pulsating machine just by, watching its surface wiggle.
Yeah, that's pretty much the challenge astronomers have faced.
Exactly, and that's what we're tackling today, these incredible wobbly stars.
And that's our mission. We're digging into a bunch of sources to uncover the secrets of these variable stars, especially the ones we call non-radial pulsators.
Non-radial pulsators. Good.
Yeah, what makes them so different? And crucially, how are new observations, especially from the Gaia mission, really shaking up our old ideas about what goes on inside stars?
So we're getting the inside scoop today.
We are indeed giving you the shortcut to understanding them.
Okay, let's unpack this then. When we talk about variable stars, what does that actually mean? I mean, what kinds of stars are we looking at that aren't just shining steadily?
Right, so fundamentally, variable stars are just stars whose brightness changes over time when we look at them.
Okay.
And we basically put them in two big buckets,
Yeah.
extrinsic and intrinsic.
Extrinsic and intrinsic. Got it.
Extrinsic ones appear to change brightness because of something external, maybe another star passing in front, eclipsing it, or big star spots rotating into view, things like that.
Ah, so it's not the star itself changing fundamentally.
Exactly.
So we're focusing on the intrinsic ones, the stars that are genuinely, flickering or pulsing. What's going on inside those stars?
Precisely.
Mm.
Now, if you set aside the really dramatic stuff like supernovae,
Right, the explosions.
yeah, there's this huge class of intrinsic variables called pulsating stars. And many of these, like the famous Cepheids, they get brighter and dimmer in a regular cycle.
They're breathing.
Kind of, yeah. They expand and contract.
Mm-hmm.
And this breathing is driven by something called the kappa mechanism.
Kappa mechanism.
Basically, energy builds up inside, but it gets trapped by gas that's really opaque. It can't get out easily.
Yeah.
So the star swells up, cools a bit, the gas becomes less opaque, energy escapes, and it contracts again. Then repeat.
A cycle.
A cycle, exactly. And different types of stars do this. You've got Cepheids or RR Lyrae stars, Delta Scuti stars, even the really massive Beta Cephei stars.
Mm-hmm.
They all use some version of this internal valve.
And different elements cause the blockage, like helium or iron.
Yeah, the specific elements involved, like ionized helium or changes in iron opacity, depend on the star's temperature and mass. And that difference in sort of the drumbeat of the pulsation gives us clues about what's deep inside.
Okay, that makes sense for the breathing stars. But you mentioned another type, the non-radial pulsators. That sounds
Yeah.
weirder. What makes them different?
Yes, this is where it gets really fascinating. With non-radial pulsators, it's not just the star's radius changing uniformly, like inflating and deflating a balloon.
Yeah.
No, the star's entire shape changes. Imagine like a blob of jelly jiggling in really complex patterns. Some parts might be moving outwards while other parts are moving inwards all at the same time.
Whoa.
These wobbly motions are driven by what we call gravity mode pulsations or G modes.
G modes, okay. Different from the pressure-driven ones in the breathers.
Exactly. If the breathers are like sound waves or P modes echoing through the star, these G modes are more like deep, slow, internal ocean waves sloshing around, often deeper inside the star.
So a star could be doing both, rippling on the surface and sloshing inside at the same time.
Theoretically, yes. That's one of the mind-bending possibilities.
Hmm.
Models predict that some stars could show both the shorter period P modes of, say, a Delta Scuti star and the longer period G modes of a Gamma Doradus star simultaneously.
That's incredible complexity. So what kind of stars are we usually talking about for these non-radial, these G-mode pulsations? And why have they been so hard to pin down?
Right. So on the main sequence that stars fusing hydrogen in their cores, we're mainly looking at intermediate to high-mass stars,
Yeah.
heavier than our sun,
Like how much heavier?
generally above about 1.3 times the sun's mass. Astronomers label them with spectral types O, B, A, and F, basically the hotter, brighter end of the main sequence. O and B stars are the real heavyweights.
And these are different inside than the sun.
Very different. Unlike our sun, which has a radiative core and a convective outer layer, these more massive stars tend to have convective cores, think boiling, churning centers, and radiative outer layers.
Okay, so that churning core makes things complicated.
Hugely complicated. It makes their internal physics really difficult to model accurately. We use asteroseismology, studying the star's vibrations, its wobbles, to try and see inside.
Starquakes.
Essentially, yes. But predicting and observing these tiny, often multi-periodic G-mode wobbles has been a massive challenge. The theoretical models are incredibly complex, and frankly, we just haven't had enough detailed long-term observations of enough stars.
That sounds like a perfect storm of difficulty. Complex models, tiny signals, not enough data. How on earth do you even start to untangle that? What changed?
Well, that really gets to the heart of it. How do we get enough good data? And this is exactly where the Gaia mission comes in.
Ah, Gaia. Famous for mapping the galaxy, right?
Absolutely. It's creating this incredible 3D map of, like, a billion stars. But the key thing for this problem is how it maps them.
How so?
Gaia measures the brightness and position of stars repeatedly over many years with extraordinary accuracy. So while its main job is mapping, this continuous, precise measurement of brightness, what we call multi-epoch photometry, makes it an absolutely fantastic tool for finding and studying variable stars, even those with really subtle changes.
So even though the wobbles are tiny, Gaia's seeing them.
It is. Its photometry, combined with the astrophysical parameters it derives for each star, things like temperature, luminosity, which lets us place them accurately on that HR diagram, that stellar census chart.
The Hertzsprung-Russell diagram, right? Temperature versus brightness.
Exactly. That combination allowed scientists to finally detect huge numbers of these non-radial pulsators and see precisely where they live on that HR diagram.
Okay, so the moment of truth. What did Gaia actually find? What was the big reveal?
The big reveal, you could say, came from a major study in 2023 by DeRitter and colleagues. They sifted through, get this, over 450,000 variable stars from Gaia's third data release.
Wow.
They managed to identify the main way about 100,000 of these intermediate and high-mass stars were oscillating. But the really groundbreaking part, they found over 10,000 new non-radial pulsators, mostly the SPB and gamma Doradus types we mentioned.
10,000 new ones, just like that.
Well, not just like that. It was a huge analysis effort. But yes, a massive increase in the known numbers.
Yeah.
And the aha moment came when they plotted these new discoveries on the HR diagram.
What did they see?
Thanks to Gaia's super accurate distances, they could place them precisely. And what they saw was that these stars, these non-radial pulsators, occupy a much wider zone on the main sequence part of the HR diagram than the existing theories predicted.
Wider. So the theories had drawn the lines too narrowly.
That's exactly it. The theoretical instability strips the zones where we expected these specific types of pulsations to happen were just too restrictive based on the older models. Gaia showed the reality is broader.
So more stars are wobbling in these complex ways than we thought possible.
Yes, the boundaries are fuzzier, more extended, especially in the region between the SPB stars and the Delta Scuti stars, and also out beyond where we thought the Gammador stars stopped.
Fascinating. Does it tell us why?
The precise borders depend on complex physics inside the star, things like how fast it rotates, how elements settle or get pushed up by radiation, how layers mix. Gaia's data doesn't instantly solve all those theoretical puzzles, but it gives the modelers crucial new constraints. It shows where their models need adjusting.
And you mentioned rotation playing a role.
Yes, that was another really neat finding. Many of these newly found pulsators had wobble frequencies that match up with what you'd expect from stars spinning pretty quickly. These are called gravito-inertial modes.
Like a spinning top wobbling.
Kind of analogous, yeah. It's a specific type of oscillation that's influenced by both gravity and the star's rotation, the Coriolis effect. And they even measured how much rotation boosts the amplitude, the size of these wobbles. Yep. About 46 micromagnitudes increase in amplitude for every extra kilometer per second of rotation speed.
Wow.
That's incredibly detailed information to pull out of the data.
Wow. Okay, so stepping back, what's the big picture here? What does this Gaia discovery mean for how we understand stars? It sounds like it's doing more than just mapping. It's like peering into their hearts.
I think that's a great way to put it. Gaia is forcing us to refine our understanding of stellar interiors. And while the analysis of its time series data is still ongoing, we'll get even better data over a longer time span.
More data always helps.
Always. It's going to lead to much tighter classifications, better placement on the HR diagram, maybe finding even fainter secondary pulsation modes, all of which feeds back into improving those complex theoretical models.
And this gravito-inertial asteroseismology you mentioned.
Right. It's still a young field, only really modeled in detail for a few dozen stars so far, but it holds this incredible potential to give us super precise masses, radii, even ages for these stars, things that are really hard to determine otherwise, especially for single stars. Gaia has absolutely shown it's a key player in pushing this field forward.
It's just amazing, isn't it? A mission designed primarily to measure where stars are is ending up telling us so much about their internal physics just by watching them wiggle.
It really is.
Oh,
And, the researchers themselves summed it up perfectly. They basically said, look, Gaia wasn't even designed to find these non-radial wobbles.
right.
But because it collected so much data so consistently and treated it all the same way,
Okay.
it revealed this huge population of new gravity mode pulsators. And crucially, their basic properties line up perfectly with the gold standard examples we knew about from dedicated planet hunting missions like Kepler, which were designed for this kind of photometry.
So the unexpected discovery confirms what we already suspected, but on a massive scale.
Precisely. It's a beautiful example of how just gathering vast amounts of precise, uniform data can let the universe tell you things you weren't even specifically asking. You just have to be ready to listen.